Let us start lecture 4, and the course is phase diagrams in single component and binary systems. And in the last lecture, we started discussing about macro state, and we could see that a system existence is clearly understood if we fix some of the parameters or variables. Like in case of single component system, if we fix pressure and temperature, and definitely that would allow us to understand the specific existence of a particular system. Now, macro state is actually a kind of a average variables of the system. It actually depends on average variables of the system. It does not consider what exactly is happening to individual particles of the system. Now, when we talked about binary systems, we saw that we need to know composition also. But when we talk about pressure and temperature in case of single component system, or a kind of mixture of components, mixture of let us say I take two component system and I fix the composition, and let us say it is forming single phase, then also I would be able to decide the existence of a particular system, thermodynamic system perfectly, no problem about that, if we fix pressure and temperature. And now, if I consider let us say ideal gas, then if we fix pressure and temperature, then of course, volume also gets fixed. So, now how volume changes with the change in pressure and temperature, if we look at that part carefully, and then we can clearly see that how volume becomes a kind of function of pressure and temperature in case of single component system, or in case of a fixed composition single phase system, then we can definitely know what is the volume. Okay. So, we need to worry about, or we need to take into our consideration about two independent variables. It can be pressure and temperature at this moment. We will see whether we can actually vary pressure or volume or temperature and volume. So, we will see later on. But let us understand how volume is a function of pressure and temperature. So, in order to understand that, that would allow us to understand the macro state much more clearly. Okay. So, let us look at a kind of a graphical representation of variation of pressure and temperature as well as volume when a particular macro state, let us say state 1, it goes to state 2. Okay. So, that is what we have taken the topic. We will continue with our topic, which is definition of important terms, and today we will introduce another important concept, which is equilibrium. So, now this equilibrium concept will cover a lot of, I think we will cover this particular equilibrium concept till the end of this particular course, because that would tell us the equilibrium between different phases. Okay. And that is what we call it a phase equilibrium. So, now let us start discussing macro state little more, and how the volume changes if a macro state 1 it goes to macro state 2 with the help of pressure and temperature change. So, macro state, so we are taking macro state, and for our easy to understand system, we take an ideal gas. So, ideal gas is such that where interaction of its constituents, or let us say molecule, is nil. Okay. Fine. So, we are taking an ideal gas. So, at the same time we are actually considering a 3-dimensional schematic diagram. This is temperature axis, this is volume axis, this is pressure axis. So, let us say I am at state A, macrostate A, macrostate 1 let us say, and I have to go to another macrostate which is 2 let us say. In order to go to macrostate, I take different path let us say. I take a path like this, I can go to position A and then I can come back to position 2. So let us say this is my position. So, I can go to A and then I can come back to 2, or I can take another path which is basically B and then I can go to 2. So, this is one path and this is another path, and let us see how temperature pressure changes when we go from 1 to 2 via A or via V. So, I can take different volumes. These are the corresponding volume V A, V 1, V B, V 2. And now, I am changing my macrostate position from 1 to A using a constant temperature path, and then let me just draw it first and then we will understand. So, I can take this is the position of 1 and then I can have another position of A, this is the position of let us say 2. When we project it on PT plane, so I can have a transformation from A to 2 via a constant temperature path, and whereas I can take 1 to 2, 1 to A via constant pressure path. So, this is my constant pressure path. Let me just put a different color. This is constant pressure path. Now, so that means first if I follow 1 to A to 2, this is 1, this is 1, this is 2, this is A. When we project it on PT surface, so from 1 to A we are following constant pressure path, and then A to 2 constant temperature path. So, and this is let us say T 1, this is T 1 temperature, T1 temperature, and this is P1 pressure. This is T1, and since it is passing to 2, I can put it as T2, and then on if I try to take B projection, I can come to this. So, this one would be again a constant pressure path. Okay. So, now this is P2. Now, if I follow 1 to B to 2, my corresponding pressure and temperature change would be first process when I go 1 to B via a constant temperature process, and then this becomes my B position. Then it takes me from B to 2 via constant pressure process, and from A to 2 is a constant temperature process. So, this is the process I am following. So, now if I follow two processes, let us say 1 to A to 2, and each one has are considered to be different microstates, sorry, different macrostates, not microstates, sorry, do not take microstate at this moment, everything is based on macrostate, because we are considering average property of the system. Now, this one, if I try to understand what is the volume change, this becomes V 2 minus V 1, this is my final change of volume. So, this becomes del V. So, how do I, and remember in case of thermodynamics always it is final minus initial state. This is my final state, final volume, this is my initial volume. Okay. So, it can be broken into two parts, be broken into these two parts, one path and the second path. So, one path could be, this can be, first path could be V A minus V 1, and then it is a cumulative. So, V 2 minus V A. Okay. So, I am saying I am seeing the total change. Okay. So, that case it becomes again you see V 2 minus V 1. So, this one if I try to put it in terms of differential form, I can write del V equal to first path is, if I see 1 to A is a constant pressure path. So, it is a variable, it is a constant pressure dt, and temperature changes from 1 to 2, and the second one is constant temperature path, this is basically P 1, and this one is P 1 to P 2 dP when the temperature is at 2, which is constant dP. Similarly, if I take a path which is 1 to B to 2, then I can write I can break into two paths, these two paths, VB minus V1 plus V2 minus VB. So, now this process is now, in this case this process is constant temperature process. So, I can write it as P1 to P2 del V P1 to P2 del P T1 del P plus, this is constant pressure process, second one, this one is a constant pressure process. So, T1 to T2 del V del P del T P2, and here is a T1. So, dt. Okay. So, now you see we are actually getting the final change in volume whether I take path 1 to A to 2 or 1 to B to 2, both the cases this is, let us say this is via B, this is via A. So, I could see del V via A equal to del V via B. So, that means V becomes complete differential. So, it becomes path independent, fine. So, it suggests that whichever path I take, I would go to, I will have a same change in volume if a macro state changes to another macro state. Now, during the transit, for example, if the system goes from 1 to B, during the transit, I have no idea how those parameters are there, what will be the parameter value. Of course, it will lie on that line, on those lines the paths, but until and unless it reaches to the particular position, I cannot specifically tell its variable conditions. So, now that suggests that let us say if the system is at 1, macro state 1, I know P 1, V 1, T 1, all three variables are fixed. Okay. So, fixed means unchanged, fine. And when that is unchanged, I could see that the system is also unchanged. Okay, fine. So, now if we leave this system on itself by fixing those variables which are deciding the very existence of the system with a definite understanding or definite recognition that what will be its pressure, volume, temperature. So, that system if it is left to itself, it would also not change from its position. Okay. So, it will stay there. So, that is the very concept of equilibrium. So, that means all the places we have those variables as fixed. It also suggests that the system would also not change if we fix those variables. Let us say point 2 or the macro state 2, I am fixing V 2 T 2. So, these are also fixed defining variables, unchanged, and state 2 also remain in state 2 without any change. Okay. So, this will also be the same. So, this is the very concept of equilibrium if we consider a single component system. Of course, if it is multi component system, the same situation can be thought about, but we have to bring in composition into picture. So, initially I do not want to bring in composition, but definitely compositional equilibrium is one of the major considerations for drawing phase diagrams in binary systems. Okay. So, now this is the concept of equilibrium. Okay. So, that means if the system left to itself under the influence of unchanging variables, the system will remain unchanged and undisturbed. Okay. Now, when we talk about macro state, these two are macro state. Okay. So, once we see the macro state, that means those macro state also talks about a state of equilibrium. So, this also talks about state of equilibrium. Okay. Since those variables are constant or unchanged. Now, as we see that in case of single component system, if I fix P and T, then definitely I am fixing the volume also. Okay. Now, in order to go, instead of going through this complicated path, so one can think simpler fashion. Let us say if I want to find out volume and if I know pressure and temperature, then I can decide, I can formulate one equation which will dictate the position, dictate the state of equilibrium of the system. Okay. So, now that equation we call it equation of state or equation of macro state or equation of the equilibrium condition of the system. So, the in case of ideal gas single component system, then I can write PV equal to nRT, where n is the size. Size means what is the number of moles of that particular gas is present in the system, and here I am considering a closed system, let us say. Okay. So, that means these becomes my equation of state. Now, instead of going through this this integration and then finding out the final volume and what is the volume change, rather than we can use this and we can easily find out the third parameter or third variable if we know two variables. So, this is equation of, so for example, I can find out V equal to nRT by P. Okay. So, that means my volume is also fixed. So, I do not need the third parameter to be specified, I only need two parameters to decide the equation of the state of equilibrium of a macro state. So, now once we understand this, now let us look at this equilibrium. Let us look at equilibrium. Now, once we say equilibrium, it indicates similar variables, same variables or unchanging variable. Now, if I consider pressure, so let us say I have a system, closed system, and then I have surrounding, Let us say the pressure of system P1 and pressure of surrounding, if they are equal. So, that means there is no unbalanced forces between the system and the surrounding. Then I can say that it reaches mechanical equilibrium. Fine. Similarly, if temperature same condition T, I can write T system and T instead of 2 I can write surrounding SURR in short form. Similarly, T system equal to T surrounding, I can term it as thermal equilibrium. Fine. Now, if I consider composition, let us say we have multiphase in single component, let us say. So, let us say water system, I have gas or the vapor and solid ice. Okay. Now, since it is a single component, the composition would be same everywhere. Now, that case my equilibrium would be decided by pressure and temperature, fine, because composition is not coming into picture. But if it is binary or multi-component, more than 3 component, then similar composition does not mean, or the same composition, and of course, I take multiphase. Multiphase system in binary or multi-component system, the same composition of different phases I am writing in different color, it does not indicate equilibrium. Okay. Does not indicate equilibrium. Rather, we have to bring in one particular important parameter which is called chemical potential, and the chemical potential cannot be for a phase, rather chemical potential of a component in a phase. Okay. So, chemical potential is dictated by mu or G bar, these are the notations. For example, in case of binary A and B system, let us say there are two phase 1 and phase 2. Okay. So, that case, if the system reaches compositional equilibrium, then I can say mu of A phase 1 should be equal to, it should be chemical potential of a particular component in phase 1 and phase 2, they should be equal, as well as for the other component it has to be similar situation. B phase 1 should be equal to chemical potential of B in phase 2. Then only I can say that the system has reached equilibrium. Remember, when you are considering this phase 1 or phase 2, that equilibrium, we are actually fixing the two other parameters, pressure and temperature. Now, if I go back, if I see this particular diagram, when I am going from 1 to A, then I am fixing pressure, and then I am taking volume as a function of volume change as a function of temperature. Similarly, when I am coming from A to 2, I am taking temperature to be constant and I am seeing the volume change as a function of pressure. So, that means in case of single component system, in order to find the third parameter, I am fixing one of those parameters. Okay. Similarly, here when I am taking a binary system, I have A and B, and there are variables like pressure, temperature and composition. So, that case, in order to find out composition, of course, volume is also there, but if I fix the size, if I fix the pressure, if I fix the temperature, then, and we know the composition, the volume is automatically known. But now, if I consider only pressure and temperature, that means we take pressure, temperature and composition. If three are known, definitely we know volume. So, we know volume. Now, if I fix pressure and temperature, so pressure and temperature fixed, so that case I lead to a situation where I have to see the equilibrium condition due to composition effect. And when I try to see the equilibrium effect due to composition, then I am fixing pressure and temperature, and then automatically I am having an equation between the chemical potential of components in different phases. Okay. So, this part will be talked later on. We will initially consider the single component system. When we talk about binary system, we will bring in chemical potential in a of course, chemical potential will be brought in when we talk about single component equilibrium conditions, but this chemical potential in case of binary system, it becomes little more complicated, but we will understand that. Fine. So, now as you see that we see another equilibrium which is called compositional equilibrium. This become composition equilibrium. And remember, composition equilibrium does not mean the same composition. We can have these phase 1 and phase 2 can have two different compositions. Can be composition. Okay. So, now we understand that what it means, the equilibrium means, with the help of a schematic where we can see that microstate it's nothing but a kind of state of equilibrium, and from one state of equilibrium to another state of equilibrium we can change via different path, and there will be variables which will be not dependent on path, and it is only dependent on the final values, and in our case it is becoming the volume. You can see that the pressure as well as temperature, which will also become independent of path, and those relation between those three variables, in order to find the third one, will be decided by the equation of state. And in the ideal case, ideal gas system, it is PV equal to nRT, n is the size of the system. Okay. And then we talked about different equilibrium, thermal, pressure as well as composition equilibrium. So, thermal and pressure equilibrium, it is bit easy to understand, but the composition equilibrium will deal with this in a greater details in future classes. So, let me stop here, we will continue our discussion on this equilibrium, and now we will talk about some of the basic laws of thermodynamics and try to understand one important aspect which is called internal energy, and then internal energy can be associated with the isolated system, and then only internal energy can be understood clearly. And finally, we will go to another parameter which is called entropy, and then we will try to see few more parameters coming up, and finally, we will reach out to Gibbs free energy G, and that G will be taking us to different equilibrium conditions. Thank you.